Hey guys, it's Mrs. Coleman, and today we are going to discuss molecular geometry. And by geometry, by the way, I really just mean what are the shapes that molecules can take. So first we'll discuss a theory that leads to these molecular geometries called the Vesper theory. Then we're going to talk about the electrons and what they have to do with Vesper theory and which ones we're actually concerned with. Because there's a lot of electrons in a molecule and we're not concerned with all of them. And then the third thing we're going to talk about are the possible shapes that molecules can take, or some of the possible shapes that molecules can take. And then we're going to lastly just go through some quick steps on how to determine the shape of a molecule. I mean, if you can't see them, how do you know their shapes? There must be a way to do that. So let's talk about what Vesper is. Vesper stands for valence shell electron pair repulsion. And what Vesper states is that the electrons surrounding the central atom in our molecule will position themselves. Remember, these are three-dimensional objects, so in three-dimensional space to be as far from each other as possible. And the reason they do that is to minimize the repulsion between these electrons that are surrounding that central atom. So for example, if you have, say, a water molecule, our central atom is our oxygen, and there are 4 sets of electrons that surround that oxygen in this compound. So those are our valence shell electrons, and they will position themselves so that they are as far from each other as they can be in three-dimensional space, while at the same time staying within the molecule. Now remember, they want to stay there because they like the protons in the nuclei of our central atom. They just really don't like each other. All right, so let's talk about which electrons in a molecule we're concerned with. So first of all, we are only concerned with the electrons that surround the central atom. And there are basically 2 types of electrons that you will find around the central atom. The 2 types are the bonded electrons. So up in our water molecule up here, these are the electrons that are being shared between the oxygen, our central atom, and the outer atoms. So there are 2 pairs of bonded electrons. And then there's the lone pairs of electrons. So these are lone pairs. They are unshared. And together, if you add up the bonded electrons, or the bonds, and then the lone pairs of electrons, these are called electron domains. So as an example, we'll use the water molecule above. So we're going to talk about that water molecule. So we'll first talk about the number of bonded pairs. So there are 2 bonds, or bonded electrons, or pairs of bonded electrons. So there are 2 bonded pairs, and there are 2 lone pairs, 1, 2, and that gives us a total of 4 electron domains. There are 4 groups of electrons surrounding this oxygen. At this point, I would like to note that lone pairs of electrons, the ones that are not bonded or unshared, these ones tend to have more repulsive force, so they repel more strongly than a bonded pair. And the reason for that is that these lone pairs up here are, they just have, I'm going to circle them. they're not trapped between two atoms. They're kind of free to roam, or a little anyway. And so they just push a little bit more on these bonded pairs than these two bonded pairs would push on each other. So at this point, we're going to talk about the possible molecular geometries or shapes that molecules can take on. And this is all, again, going to be due to the number and types of electron domains that you find around the central atom. Number means you know how many, and type means are they bonded or unbonded or lone pairs of electrons. Those different types of electrons and how many there are around the central atom is going to determine the shape of a molecule. Now I'm going to, you should fill out the paper that I gave you, the molecular geometry table that I gave you as you go along, because that will serve as your notes for these possible molecular shapes. I would also like to note that there are a lot of different molecular shapes that I am not making you know. I am making you know 9 possible shapes. So let's go ahead and start with a molecule that would have a central atom with 2 electron domains surrounding it. So this kind of molecule with 2 electron domains on your central atom really just means that you have 2 atoms bonded to your central atom. So I have 2 examples. I have beryllium hydride and carbon dioxide. So BeH2 and CO2. Now on your notes, I already filled this in for you, so you can just kind of follow, or at least this particular one I filled in for you using carbon dioxide. But I wanted to give you a second example. So what you'll notice is that you have your central atom in both, and then 2 atoms bonded to the central atoms. So that's 1, 2 electron domains, 1, 2 electron domains. And I want to point out that a double bond is just 1 electron domain. Even though it's a double bond, we still count it as just 1 group of electrons surrounding the carbon, and then over here we have another group of electrons. So they both have 2 electron domains. Now, the best orientation for this kind of molecule is to have these electron domains 180 degrees from each other. So you need to list the bond angle. So that's called a bond angle. You'll notice there are 0 lone pairs of electrons, right? If there was a lone pair, you would see them. And the name for this type of molecular geometry is linear. So a linear orientation, of course, is where your atoms are on a straight line. And that makes sense because our central atom has 2 electron domains. If they're 180 degrees from each other, that would make a linear molecule. So the next possible molecular geometry is based on having 3 electron domains around your central atom. And those 3 electron domains can either be 3 atoms bonded to our central atom and no lone pairs on our central atom, or 2 atoms bonded and 1 lone pair for a total of 3 on both 3 electron domains. So let's focus on the first one, where you have 3 atoms bonded to your central atom with 0 lone pairs. So boron trihydride, for example, BH3. So you've got your boron in the middle, and there are 3 atoms bonded to it for a total of 1, 2, 3 electron domains, and there are no lone pairs on our central atom. In this case, the best configuration or orientation you can get is for the molecules to be in this triangle, like flat, sort of flush to the paper or one-dimensional, well, 2-dimensional triangle. And the bond angle is 120, so you need to make sure that you list that the bond angle is 120 degrees, which makes sense, right? Because a circle is 360, and a third of that is 120. The name of this is called a trigonal planar. So trigonal planar geometry is, again, it's trigonal because it's like a triangle, and planar means that all the atoms are flush with each other. They're in one plane. And the other 3-electron domain shape that you can get is where you have 2 atoms bonded to your central atom and only 1 lone pair on the central atom. So, for example, ozone, which has O3 as its chemical formula. So ozone has 1 central atom and 1, 2, 3 electron domains around the central atom. So over here, same thing. But one of those electron domains is a lone pair. So you still get your 120-degree bond angle that we had over here. So you still get about 120-degree bond angle. It'll be slightly less. I don't expect you to know that. I just expect you to know that it's around 120. Now, why is it slightly less? Well, if you remember me telling you that lone pairs of electrons take up more space, so that's going to push these 2 pairs slightly closer to each other. So it's really more like 116, but we're going to go ahead and say it's fine if you tell me that it's 120. And the name of this is a bent 120 molecular geometry, because the molecule ends up bent. Remember those electrons over here, which they don't show on this particular structure. There are electrons here that are pushing these bonds closer to each other. So it makes a bent molecule. So the next kind of geometry is based on having 4 electron domains. So you could have all of those electron domains being bonded electrons. You could have 3 of them being bonded and 1 being a lone pair. Or you could have 2 atoms bonded and 2 lone pairs. So let's go ahead and talk about the 4 atoms bonded first. So an example of a molecule with 4 atoms bonded is carbon tetrahydride, also called methane sometimes, so CH4. So your carbon is your central atom, and there are 1, 2, 3, 4 atoms bonded to it, which makes 1, 2, 3, 4 electron domains. All of them are bonded, and there are 0 lone pairs. This shape, because this is a 3-dimensional object, it's not in a 2-dimensional space, you end up with bond angles of 109.5 degrees. Remember, you have more than just the flat 2-dimensional space to work in, so you're not going to get 90-degree bond angles. You're going to get bigger bond angles, 109.5. And the name of this molecular geometry is called tetrahedral. So tetrahedral. So another 4-electron domain molecule is something like ammonia. Ammonia is not, of course, the only one, but that's just an example. Ammonia, also called nitrogen trihydride, is a nitrogen bonded to 3 hydrogens. So again, you have your central atom, and in this case, you have 1, 2, 3, 4 electron domains. 3 of them are bonded, and 1 of them is a lone pair. So similar to this tetrahedral over here, you're going to get bond angles of greater than 90 degrees, but you'll notice on this one the bond angle is about 107 degrees. And the reason why is because, remember, this lone pair of electrons pushes on the bonded electrons a little bit more because it takes up more space, pushing them a little closer together. So you get a bond angle of a little bit less than 109, about 107. You actually do need to know the bond angle of 107. You don't have to have the 0.3 on there. The name of this shape is called trigonal pyramidal. So trigonal pyramidal. So it looks like a little pyramid, and at the top of the pyramid you have this lone pair of electrons. All right, and then let's talk about the very last one with 4 electron domains. On this, we have 2 atoms bonded to our central atom, and then 2 lone pairs for a total of 4 electron domains. Our example here is water, H2O. And again, because now you have, instead of 1 lone pair pushing on these bonds, you now have 2, and that's going to push these bonds a little closer to each other than they were pushed over here. So you're going to get a bond angle of about 104 degrees. And you'll notice that your molecule is a bent molecule. But this case, it's bent with about 104 degrees Celsius, degree bond angle. So this is actually referred to as a bent 109.5. The reason being that it's based off that tetrahedral shape with a bond angle of around 109. I realize that it's less than that, but that's just what they call it, is bent 109.5. Okay, so now we're at 5 electron domains. And there are a number of shapes that can take place with 5 electron domains. I'm making you know one of them. So the one that I'm making you know is where all 5 domains are bonded electrons, so no lone pairs on your central atom. The example I'm going to use is phosphorus pentachloride, and phosphorus in our example is our central atom, and there are 5 electron domains surrounding the phosphorus. All of them are bonded. There are 0 lone pairs. So remember, this is a 3-dimensional object, and it's going to have 2 bond angles. So the bond angle between this and this is 90 degrees, and then of course the bond angle that you would find between this chlorine or this atom and this atom is 120 degrees, just like it said on the picture, just a little hard to visualize. So that is the only 5 electron domain shape I'm going to make you know, and its name, which is already written right here, but I'll go ahead and write it again, is trigonal bipyramidal. There you go. Now, you may have noticed, and I don't know if you did, that your central atom in a trigonal bipyramidal, or something with 5 electron domains, would have 2, 4, 6, 8, 10 electrons surrounding your central atom. So it should be noted that a trigonal bipyramidal violates the octet rule, because it puts 10 valence electrons on your central atom. And Ca is central atom. So that is something that you will see from time to time. So just know that if you have extra electrons and when you're drawing a Lewis dot structure, you would just throw them on your central atom, and it's probably going to be something that violates the octet rule. All right, and the last number of electron domains that we're going to look at are molecules that have 6 electron domains on the central atom. And there are a number of these as well, and I'm making you know 2 of them. So the 2 I'm making you know are a molecule where the central atom has all 6 of its electron domains as bonded electrons, no lone pairs. So an example of this would be sulfur hexafluoride. You may know or have heard of sulfur hexafluoride, just on a little side note. It's the gas that when you inhale it, it actually makes your voice go really, really low because it's super dense. You may have seen videos of people doing that. Anyway, this is sulfur hexafluoride. And you'll notice again, sulfur is your central atom in this example. So central atom has 1, 2, 3, 4, 5, 6 bonded atoms, 0 lone pairs, so 6 electron domains. And the name of this particular shape is octahedral. So it's an 8-sided molecule, or it has 8 sides. So octahedral. And then the last molecular geometry you will need to know is where you have 4 atoms bonded in 2 lone pairs, so a total of 6 electron domains. So something like xenon tetrafluoride would form this particular shape with xenon as your central atom, and then there are 1, 2, 3, 4 atoms bonded, and then 2 lone pairs. So it's going to take exactly the same shape as one where you have 6 electrons bonded to your central atom, or sorry, 6 atoms bonded to your central atom, only you're missing, instead of these being atoms bonded, they're actually lone pairs. And so your molecule ends up with your atoms and your bonds all being in one plane of existence in a square shape. So bond angle on these all the way around is 90 degrees. So 90 degrees between your bonded atoms. And the name of this shape is square planar. Square because your atoms form a square with one another. Planar because those are all on the same plane, or they're all flush with each other. And again, I just want to point out that if you have atoms with, or rather molecules with 6 electron domains surrounding the atom, you are going to have 2, 4, 6, 8, 10, 12 electrons that surround that central atom. So again, this is going to be a violation of the octet rule, having your central atom surrounded by 12 valence electrons. Sulfur does that a lot, so do your noble gases. All right, and last but not least, how do you determine the shape of a molecule based on, of course, its chemical formula or on its Lewis dot structure? So most of the time you're going to be given a chemical formula. For example, you might be given the chemical formula PF3, and I'm going to ask you to, or I will ask you to determine the shape of this molecule. So the first thing you're going to want to do is draw the Lewis dot diagram. In order to draw the Lewis dot diagram, you need to add up valence electrons, and then, place those valence electrons around your central atom and the flanking atoms. So here would be the correct Lewis dot structure. You should know how to do that by now. The second thing you're going to do is you're going to count the electron domains. So around our central atom, remember, so here's your central atom, phosphorus, and there are 1, 2, 3, 4 electron domains around your central atom. And then the next thing you're going to do is determine if those domains are bonded or if they're lone pairs, and that's pretty easy from your Lewis dot structure. You can see that there are 1 lone pair and 3 bonded. So you've got 3 bonded atoms and 1 lone pair. And then you're going to look it up on the table that you just filled out, and you will find that the shape of this molecule with 3 atoms bonded and 1 lone pair gives you a shape of trigonal pyramidal. So in fact, this molecule looks not T-shaped like this, right, because we have it drawn like a T, but instead it would look something more like this, with your phosphorus and your fluorines forming kind of this fun little, pyramid shape. And then those lone pairs of electrons on the phosphorus are responsible for pushing those electrons or in the bonds down, making it more of a pyramid shaped. And if I were to ask you the bond angle on this, hopefully you would indicate that we have a bond angle of about 107 degrees.